briefly introduce my broader research agenda. My work focuses on three major directions. First, I study how to optimize public transport operation. Second, I look at how emerging mobility technology can improve accessibility. Third, I work on the resilient transportation system, especially under disruption and disaster. So whether we are talking about transit fare, shared mobility, evacuation planning, or infrastructure recovery, the common thing is the same. How do we make transportation system more efficient, more equitable, and more resilient? One major part of my research looked at the infrastructure investment under uncertainty. Transportation systems are expensive, long-term, and full of uncertainty. Demand change, city grows, and technology evolves, and sometimes planners make decisions while hoping the future behaves nicely, which unfortunately it rarely does. So in this line of work, I study questions like when should we expand a rail line? How long should that line be? When should airport increase capacity? And how do we make this decision when demand is not stable? This background is important for today's talk because the delivery switching problem is really another version of the same question. How do we make operational decisions when the future it is uncertain? Another part of my work focuses on the policy and operational design in public transportation. For example, I have studied time-independent transit fare, transit regulation, subsidization, and switching between fixed and flexible transit service. One interesting result from that work is sometimes the best policy is not what we would intuitively expect. For instance, under certain conditions, the optimal fare can really be zero. But so occasionally, the max is more generous than the transit agency budget office. So this research also introduced me the idea of switching threshold, that systems not always move smoothly from one mode to the other. This could be hysteresis. That can be switching costs and the timing matter. So this idea directly motivates today's study on switching between track only and the Journal 6 track delivery. I'm also interested in the emerging technology in transportation, including the AI, robotic, and even quantum computing application. So these include the work such as vehicle occupancy estimation using the Wi-Fi probe data, and robotic assist track delivery and other intelligent transportation systems. What connected this topic is not just the technology itself, but the decision problems behind it. When does the new technology actually create value? Because adding technology is easy. Adding useful technology is the harder part. And that's exactly why this drone delivery work matter. Drone may look very cool, but in real challenging is figuring out when and where they make operational and economic sense. In addition to efficiency, my research also emphasized the equity and resiliency. For example, I have worked on bridge and roadway restoration planning and evacuation strategy using the shared autonomous vehicle. This perspective is especially important for delivery system. Access to the food, medicine, and essential goods is not only a logistic issue, it is a community resilience issue. It's a system of is efficiently or already well-served area that it is not solving the food problems. And this slide is showing some of the stakeholders and projects shaping my research ecosystem. I have been fortunate to work with agencies like university and sponsors, including FDOT, NSF, USDA, UTC program, and other research partners. What I appreciate most is this collaboration keeps our research grounded in the real-world problem. So this project also comes from the same spirit, development and analytical tools that can help support practical decision in the real delivery system. So now let me turn into the main motivation of these projects. Food insecurity remains a major issue in the United States, and many households still facing serious barrier to accessing the healthy food. In food desert area, residents may need to travel long distance to reach the full service grocery store, which increasing the time and the transportation burden. So the question is, how can new delivery system can help reduce this access gap? So this is where vehicle and robot collaboration become promising. If it's well designed, it could improve the food access when also reducing the delivery costs. In other words, the goal is not just faster package delivery. It is using the logistic innovation to address the real social needs. One common strategy for improving food access is better connect the transit service with grocery access. This approach absolutely helps, especially for transit-dependent population, but it also has some limitation. Not every low-income resident rely on the transit alone, and rural area also always have a very limited service frequency and the lower accessibility. So while public transit can be part of the solution, it is not always enough by itself. This is why we began to ask whether a collaborative delivery system combining the traditional vehicles and autonomous technology could offer a more flexible and scalable solution. This brings us to the core research question behind the broader projects. First, is the food access distributed equitably, especially in the disadvantaged community? Second, can collaborative vehicle and robotic delivery system can improve food access? And third, can such a system produce a meaningful cost saving and society economic benefits? Our central hypothesis is that by coordinating this large vehicle with a smaller autonomous robots, we can create a system that can both more efficient and more adaptable. So today's the talk focused on one key pieces of that vision, how to determine when to switch between the truck only and drone assist delivery as the demand change over time. So here we illustrate the idea of the collaborative delivery. The concept is that a conventional vehicle handles the heavier long-distance part of the route, while smaller drones can handle some of the last-mile delivery. So this allows each mode to do what is the best at. Truck provide the capacity and long-haul efficiency. Drone provide the flexibility and speed for final delivery. You can think of it as a teamwork. The truck does not need to do every small task, and the drone does not need to pretend it is a truck. So this research can also feed directly to education and outreach. We integrate the research finding into course and also student projects and post-competition field trips and collaborative activity with external partner. I care a lot about this connection between research and teaching. Students should not only learn theory from the textbook, they should also engage with the real problem that agency and communities actually facing. In addition to the analytic modeling, we are also exploring the immersive learning tools such as the visual reality. So let me open the link I uploaded, which showing the records in our VR system development. This VR system allows the student and a researcher to simulate the delivery system.
I think it's not showing on the share screen.
I see. Let me reshare. for demonstration, we also have some using the drone for operation using the VR system, and it is still the we are trying to offer this using the VR for drone operations into the course design, curriculum design. Okay, so back to the slides here. So for this drone-related delivery system, so this VR can help, especially useful when real-world testing and operation could be very expensive, constrained, or risky. And we could have this simulated environment which can let us to experiment and fail safely and learn faster. So unlike a real drone, visual drone can much less likely upset this building manager. So here, let me introduce the two delivery modes considered in this study. The first is the truck-only delivery, which is the traditional and still dominant approach in logistics. The truck has the large capacity and perform well over long distance. The second is the drone-assist truck delivery. When the truck and the drone work together, in this mode, drone can help handle the last mile, which is often the most time-consuming and expensive part of the process. So the trade-off is clear. Truck-only delivery system is simple and robust, while drone-assist delivery may be faster and more efficient under the right condition. The challenging is that the right conditions do not stay fixed. Demand change, and that is where the switch problem begins. So this represents the key question of our research. We asked, when should the system switch between truck-only and drone-assist truck in order to maximize the benefit? To answer this, we examined the four types of model: a static model, myopic dynamic model, and deterministic dynamic model, and the stochastic dynamic model. The progression here is intentional. We start simple, then gradually add more real lessons. This is also how many research projects goes. Our research make four main contributions. First, we established the cost function for the two delivery mode using continuous approximation model. Second, we model demand density as an uncertain factor using the geometric Brownian motion. Third, we develop myopia and deterministic model. And fourth, we extend this into a stochastic dynamic switching model using a market entry access real optional framework. Finally, apply the model to a real-world case in the Miami-Dade County for major logistics operator. So the contribution is both methodological and practical. We build the theory and then we test whether it is actually help in a realistic settings. This figure showing the comparison between two delivery mode in truck-only delivery. The truck handle both the long-haul movement and the final customer delivery. That means the driver is responsible for packing, loading, and unloading, and completing each stop. In drone-assist truck delivery, the truck still performs the main movement from the depots, but the drone are launched near the delivery point to complete some of the final delivery. An important detail is that the truck does not necessarily need to wait during every drone delivery. This creates the opportunity for time saving and operational efficiency. So conceptually, the drone assist system allow the parallelisms, and the engines loved parallelism much they loved equations. To model this delivery route, we use the continuous approximation models. We assume the delivery room is a compact region and demand points are randomly and independently distributed across the service area. This allows us to approximate the route structure without having to specify every single street or customer point. In other words, instead of tracing every delivery point one by one, we model the overall pattern in a chartable way. So this is very useful when the goal is just a strategy analysis rather than an exact real-time routing. Now we move to the cost formulation. In each delivery mode, the total cost per per customer include two components. First is operational cost per unit distance, and second is the stock cost per the delivery point. For truck-only delivery, the truck bear the entire burden of both the travel and the stock activity. For Jones 6 delivery, some of those costs are shared between the truck and Jones. This equation may look complex, but they capture the core economics of the system. Distance matters, and stock matters, and division of the neighbors between truck and Jones matters. Basically, delivery is not just about a moving package. It's about paying every mile and every stop along the way. Using the per customer cost, we then calculate the total cost over the whole service zone. This is done by combining average cost per delivery point with overall demand in the service area. That step is important because operators do not care only about a single delivery point. They care about the total system cost across the region. So at this stage, we move forward from the local delivery behavior to the system level performance. Once we have the cost function from both delivery mode, we can define the incremental cost saving from the operational one mode relative to the other. So this is a key measure that drives the switching preference. If the truck-only delivery is cheaper, then the saving favor truck-only. If the Jones 6 delivery becomes cheaper, then the system have an incentive to switch. So this function becomes economic signals for the operational change. You can think of it, the delivery system asks itself a question every period: am I still in the right mode, or am I just being the standby? So we begin the static model. Here we compare the cost between the baseline, the parameters value, and identify which mode perform better at different demand density. The result is intuitive. When demand density is relatively low, truck only is preferable. In that case, adding Jones can create the actual cost without enough benefits. But as demand density increases, Jones 6 delivery may become more attractive because it can improve efficiency in the last mile. So even in the static setting, we already see a social behavior. This problem is that real demand does not stay fixed, which is why we need to dynamic model. To capture the uncertainty, we model the demand density as a geometric Brownian motion model. We allow the demand to evolve over time with both the growth, trend, and volatilities. The key idea is that the demand is not perfectly predictable, and customer require fluctuate, and the customer requests fluctuate, and the demand delivery system must make decisions under demand uncertainty rather than under perfect foresight. We first consider the two dynamic switching rule, the myopic model that switch as soon as possible as the immediate cost saving favor the other mode. It is simple and reactive. If the other mode looks cheaper, right now switch. The deterministic model could improve on this by accounting the switching costs. In that case, the system switch only the benefits. Is this the switching cost structure? So this distinction is important because changing model is not free. These are the model setup fee and operational adjustment, training, and the coordination burdens. To model the switching problems more realistic, we use the market entry access real option framework. Real option theory is very useful. You might see it. It is very rare to use in the transportation area. Real option originally from the financial area. Real option is for the decision making in uncertain and dynamic environment because it can value their flexibility instead of asking only what it is cheapest right now. It asking what is optimal when future uncertainty matters. So this is a nature fit for our problems because switching model is not a one-time decision. The decision makers has the option to switch later, and that option itself it has a value. So real option approach helps us to determine not only whether switching is beneficial, but also waiting is better than switching immediately. Using this framework, we determine stochastic dynamic model. We define the option value of operating in the truck-only modes and Jones 6 mode, then using the access equivalent condition to characterize the switching problems. Conceptually, every mode has a value. and switching occurs when the value of moving to the other mode becomes sufficient high. So this gives us a very realistic decision rule when it becomes incorporate uncertainty and future flexibility rather than focus on a very immediate cost comparison. To solve the switching problem, we use the value matching and smooth pasting condition. So this condition allows us to determine the switching threshold between modes. Because switching cost exists, we does not need to just one threshold. Instead, we obtain two thresholds, one for switching up, one for switching back. This Qianwen is the resist region, meaning that the system does not switch back and forth too easily. That is desirable because the frequent switch can be costly and inefficient. In the special case when switching cost is zero, the two threshold can collapse into a single threshold. That means switching decision become more simple. One demand cross that single point. The operational switch modes. This case is useful and analytically because it can help us understand the structure of the model. This slide showing how this stochastic model behaves when switching cost is zero. There is only one threshold, so the system switch more radically as the demand cross that point. Switching cost is positive. We got two thresholds. Switching is delayed, so this reduce unnecessary switching and avoid reacting to the temporal fluctuation. So the model captures a very practical insight. Even if another mode looks slightly better today, it may still worth waiting until the economic advantage is strong enough to justify the transition. Now let us to compare the performance across models. So the result shows that stochastic dynamic model can achieve the highest cost saving compared with a myopic policy. It reduced accepted cost by 43%. This is a substantial improvement, and it shows the value of explicit modeling uncertainty and the switch timing. So this is not just a theoretical improvement. The smarter switching logistics translate into the meaningful operational saving. So far, we have focused on the switching behavior between two modes, but in a larger system, the operator may have a multiple policy option, not just two. So this introduces a multi-optional switching model that allow for the gradual transition across the service configuration. For example, instead of jumping directly from a full area truck-only service to full area of a Journal 6 service, the operator can first deploy hybrid delivery in a high-demand area while keeping the truck-only service in a low-demand area. This is more realistic for the large regions because real system does not usually transform overnight. They evolve in stage, especially when the budget are involved. And here we show how this gradual transition work. The process is to divide into two stages. First, from truck only to hybrid delivery, then from hybrid delivery to the full Journal 6 truck delivery. As the demand rises, the system moves forward through this stage. As demand falls, and it can move back down. So this switching structure is valuable because it allows the system to adapt more smoothly to heterogeneous demand pattern across the space and time. To evaluate the model in a real-world context, we apply it to Miami-Dade County, Florida, using 2021 as the basis year. We estimate the daily delivery demand density and focus on three major logistic operators, USPS, and FedEx. These firms dominate the parcel delivery in the U.S., so they provide a meaningful application context. The growth and volatility parameters are calibrated using the real market data. So now the question becomes, once we move from theory to practice, does the dynamic switching mode still create value? Fortunately, the answer is yes. So this represents a major result for the three logistic operator. For all these three, USPS, ULPS, and FADAs, both the deterministic and stochastic model outperform the myopic policy. And again, the stochastic model delivered the greatest savings. The improvements are practically strong for FADAs, but all these operators benefit from more strategy, the switching decision. So this finding suggests that dynamic switching is not just a modeling exercise, but it can produce practical gain in the real delivery system while the demand uncertain is properly considered. We also test the model option model across the Miami-Dade region because the demand is highly unevenly across space. A single uniform policy is not ideal. Some area may have the low demand and some are better served by the truck only fleets, while others may justify more during the intensive operations. So this dynamic policy adapts fleet deployment based on the local demand density, and it is shown in the result and achieve lower total cost than the static alternative. So the major takeaway here is that spatial flexibility matters, not just the temporal flexibility. To conclude, our results showing the several important findings. First, the truck-only delivery is preferable when the demand density is relatively low. Secondly, the switching costs reduce the numbers of switching events and delay the switching point. And third, the stochastic real option basis model provide a more realistic and economic effective switching strategy. And third, and the last one, but not least, in the Miami-Dade case study, the proposed model significantly improved the cost saving for the major logistic operators. So the major message is that the best delivery mode is not fixed. It depends on the demand, uncertainty, and the cost of switching. And with the right model, we can make this decision much more intelligently. So there are several directions of the future work. First, the demand may not always follow the geometric Brownian motions. We can plan to explore the mean reverting process, such as the oil process. So the oil process, instead of having like a growth rate, average growth rate or volatility rate to capture the uncertainty, we will convert into the mean value, which is highly aligned with the transportation data, as we all know has the mean average, like the AADT data, ADT data, and so on. So this mean reverting process can be calibrated by the real time the data that feed it. Secondly, we wanted to incorporate demand jumps. For example, in some of the cases, such as the disaster, just like the hurricane, it could be like the seasonal, like a storm, could be like different disasters that might affect our demands. And we might not necessarily consider this maybe just 911 or any like 2009, the financial crisis. Those large events do have an impact on the demands. So which will result in the demand from the customer might significant jump to high, or it can be like drop significantly. So the delivery system may experience sudden spike or drop, such as the COVID-19 or other disruptions. So we can make use of those jump diffusion models to capture these uncertainty of the demand. And third, we plan to jointly optimize the switching timing and the numbers of the drones mounting on each track. So far, we only consider within the 10 drones within a one track mounting to the track, and see whether multiple of a drone mounting on the track, how kind of scale of economic it can achieve. And another thing I'm currently working on paper is that we do consider the energy consumptions. That instead of saving the time, saving the travel time efficiencies, whether we can consider the energy consumption, energy aware, whether this will affect the decision making of when to switch June 6 track or just track only surveys, and in what the scenarios and different objectives that will result in the decision making could be very different. And as you know, in our family FSU, our College of Engineering, we are trying to build wind tunnels to create the experiments to capture. We are hopefully have these wind tunnel being built in the next years. In this work, we are proposing to consider the wind conditions, whether we can leverage the wind on the flying drones UAV to testing in what kind of a scenario we can make use of those wind directions for this delivery system more efficiency and environmental benefits. So yes, there's a plenty of work ahead. Fortunately, for researcher, transportation section are very generous in producing those new programs. I will keep you posted of this research progress. So I think this is much of the presentation, and appreciate the opportunity to share this work with you. If you have any questions, comments, and would like to discuss any potential work together, I'm happy to continue the conversation.
Thank you. Thank you so much. It was really good. I will, does anyone have any questions? If you guys have any questions, you can go ahead and ask, or leave a comment if you don't want to talk, but feel free. Go ahead. Dr. Chang, I saw you raise your hand.
Yeah. Okay, thank you for the presentation. It's very interesting topic. I'm just wondering, we're talking about the drone delivery. So as far as you know, what is the biggest administrative or policy side limitations regarding this? I'm not sure all the counties or agencies they're willing to actually use it as one of the method. Is there any concern that you know they may have?
Yes, that's a great question. We all know drone, it's a very cool technology. A lot of people wanted to add it, but they always come with a lot of cost and operational size, and also the policy, the implementations. And so far, based on my understanding, some of the city they do operating using the Drone 6 track. For example, the USPS, UPS, and FedEx, they do have these drone for delivery the food. And also Amazon, they do have their drone delivery system. But in the I understand there's some challenging due to the flying drone in Florida that's have some regulation and limitation, and I do believe, and it could be also looking at in the future, near future, to consider some of the region they might have the regulation that might not allow the drone flying, and some of the region it's allowed it, and whether we can consider the regulation on the different regions and how to better design for these journalistic track for delivery system. Yeah, I do agree there's quite a few limitation right now, and so far I did not see much of the application, but in the mainland China, I do see there's a quite a few business has been using the drone for flying. in the US, some of the largest cities like Miami, they do have the robotic for food
Yes.
delivery in the downtown area. But for the drone, it's still under regulation due to the safety concerns of flying, and there's some needs some the additional regulation, the policy, to do so. So those people who in the for example DPTW, those agencies still like very consultative to this implementation.
Okay, and if I understand correctly, that drone-mounted trucks, those are maybe more effective in relatively rural area compared to urban area, right?
Yeah, it depends on the case. As you can see our example here at we found that in the demand is relatively low, then truck may be more preferable. When the demand become higher, since June can like saving the last mile travel cost, it will be more favorable. And in rural area, we can all understand that the demand is relative low, and also especially the distribute and Zhong might not bring enough benefit to implement it because Zhong can so how can I say June can provide more benefit in the urban area because some of the flying last mile travel we do not need to stick to the railway network. It could avoid the congestion. So it might bring the more benefit in the urban area. So it will be also this is could give us an interesting question like in what situation in what would that be like when we're modeling in urban area and rural area, how could we formulate the cost, whether we should consider congestions, whether in what kinds of delivery system will uh, um, perform the better in different setting.
And one more question is, as far as I know, the distance that can be covered by drones is mostly limited by the battery, by the power of the drones, right? By the battery.
Yeah.
So for this truck-mounted drones, does it need extra design, specifically designed batteries, or it's okay, we just use normal ordinary batteries?
I do think that they do need a specialized battery system. In this research, we did not consider the battery, the constraint, because every package. So this is it's like an economic model. We're just trying to use a continuous approximation model to approximate the general cost instead of consider routing specifically and also the battery consumption specifically. But in the near future, as I mentioned, we are working on the green drone delivery paper. We do consider the battery constraint as like every delivery, it depends on the package weight and it consumes the battery in a different level. So we do need to consider the battery, the constraint on the delivery using the drone. As you mentioned, and also you mentioned whether this drone or six track delivery system, whether we should consider specialized battery system. Yes, it is, and I'm still like working on this aspect. I'm hoping in the near future we could consider more the like a realistic consideration. For example, how these for example, if it's a battery system using the solar system to charging for the drone, which it can be mounted on the truck. This could be a project, even it could be proposed to the Department of Energy. That's if we develop such system, this hardware setup, whether it can help to provide a more efficient way and also energy saving way for the delivery system for fridge delivery.
That's right. That's right.
Yeah,
For
I
sure.
do believe it's a maybe the promising the research and could attract some the funding agency.
I assume those trucks they should be able to charge the drones, right?
Yes. I think so.
Yes.
They will installation of the panels and to ensure the drone can be charging at the same time when it is mounted on the truck.
Yeah, yeah,
Instead
yeah.
of when it is not flying mounted on the truck, it is charging at the same time. And there's quite a few researchers. I just host a workshop with Dr. Kondo from the UIUC. She is proposing a research question on the charging the speed on the electric vehicles and how it could provide the efficiency way for evacuation. So
Hmm.
I think the methodology can also apply in this research.
Hmm.
That's consider those charging system mounted on the truck and
Hmm.
whether those drone can make full use of the time. It is also an optimization of problems.
Okay, thank you. Thank you very much.
Yes,
Yes.
thanks.
Thank you.
All those excellent
Um,
questions.
anyone has a question? Because I was kind of wondering, you said they are more efficient for urban areas because of the travel distance. It's just easier for them. But do you know if they are trying to make drone delivery more efficient or maybe more accessible in like rural areas or areas that are like more difficult to access? Because I would imagine that's like
Oh,
what it
yeah,
would
I got your
like
point.
bring more benefits, if it's like, oh, restrict the area or if something happened, some like nature disaster happened and they would use that. Or maybe it's just like a community that's kind of further away, like you
Yeah,
said, for the
yeah.
food, like healthy food deliveries, things like.
Yes, I think this framework can also apply to different scenario. As you mentioned, drone can not only provide the last mile delivery system, saving the labor cost and saving the time, but it can also helping to relieve the traffic congestion because it does not follow the roadway network, does not occupying any the roadway spacing, so it can reduce the traffic on the road, which is beneficial on the urban area. For the rural area, it is also beneficial because some of the places hard to access. Some of the, for example, the rural area, we have some terrain that's hard to climb using the truck, and maybe the drone flying will be also a beneficial way to achieve it. And you are also mentioning the disaster scenario. For example, if you are considered a hurricane king, that some of the roadway network become flooded, become inaccessible, or due to the wildfire, some of the places become region become inaccessible. Flying drone may provide a potential solution that can provide those medicines or any the food essential for those evacuees, and they are able to have those assistance on time. So those are the scenario we can apply to. I believe it will also bring very insightful, very counterintuitive findings.
Mhm. Thank you. Thank you. Um, does anyone has any other questions? Any final questions? I guess we're good then. No one has any questions. All right. Thank you so much once again.
Yeah.
Thank you for presenting and for accepting our invitation. That was a really great presentation. We don't hear much about drone on like undergraduate classes. So it's really nice to see what's going on out there. All right. And
Yes,
thank
wonderful.
you
I
so
appreciate this invitation and very grateful for this opportunity to share my research. I'm also the ITE student chapter, faculty advisor. I'm hoping to can invite you and also Dr. Chen came to our webinar hosted by our ITE student chapter. And
Yeah, we
Oh,
can talk about
yes.
that. I'll be waiting to.
yes.
Yes. Yeah, we have our IT chapter here. I'm also like a member. That would be great. It's always good to like collaborate between different
in case any
universities. Yes.
opportunity, we can work together.
Yes.
Yeah, we can also talk about how we can collaborate on this. I've also working on the drone system before, but most likely on the operation part, not on the food delivery part. But I know I do have the like background of the operation part of the drones that can be integrated in your research for sure.
That would be wonderful. I look forward to this collaboration.
All right. Thank you so much. Thank you everyone who is attending, who has attending our event. And if we're all set, I would just end the meeting now.
Okay,
Any
thank
final
you.
notes?
Yes,
All right.
wonderful.
Thank you, Dr. Guo. Thank you.
Yes, keep in touch.
Thank
Bye.
you.
Okay, keep in
Bye,
touch.
everyone.
Bye.
Bye.